The DurbinWatson versus BreuschGodfrey. Must have been another little essay. Compare and contrast, I suppose. So, in your discussion of DurbinWatson, you had to tell me that it's for a test of first-order serial correlation. And the way you do it is to save the OLS residuals and construct this test statistic. So, for example, if I wanted to turn this into a numerical question, I could give you the numerator and the denominator, or I could fool you a little and expand the square in the numerator and cancel some terms and so on and so forth. See if you can put it back together again, because you're not fooled by such simple things, devious, silly things like that. Compare the test statistic to a suitably chosen critical value. That's the next step in using the DurbinWatson. If the null is rejected, then what you have to do next is re-estimate the model using either two-step OLS or iterative maximum likelihood. Caveats for DurbinWatson. And one problem that we talked about was that there is an inconclusive region. That is, you look up in the table and you get a Durbin lower and a Durbin upper. And what happens when your test statistic falls in the inconclusive region? Well, you get some more data. It cannot be used in a model with a lag-dependent variable. Changes the structure of the test statistic when you have a lag-dependent variable. It's a test with a very specific alternative. So it's not robust against other kinds of serial correlation other than just first order. BreuschGodfrey is a Lagrange multiplier test. The null is no serial correlation. From the OLS residuals, construct the test statistic. That's a matter of memory. Where x0 is the matrix of explanatory variables augmented by p or q lagged OLS residual vectors. That's a memory problem. The missing lag values are filled in by zeros so that you retain a total of p observations. R0 squared is the uncentered coefficient of determination from this same auxiliary regression of dependent variable on that augmented right-hand side matrix. The critical value is read from a chi-square with p degrees of freedom. The principal caveat is that the distribution of the test statistic is asymptotically chi-square. As such, it's a large sample test. Another caveat that's not there, of course, is that you have to pick the degree of serial correlation that you're prepared to deal with, P or Q.